Okay, so you should already have looked at a couple of examples in the book about the probability of a union. So here are just a couple more to illustrate this. So example one, what is the probability of rolling a 10-sided die and rolling a number that is a multiple of 3 or is odd? Okay, that's the key. So let's give the events some names, okay, or the sets some names. All right, so set E would contain the elements 3, 6, 9. Set F are the odd numbers, so 1, 3, 5, 7, and 9. All right, so what is the probability of being in E or in the union? Well, we could write the union of these two things. E union F, that for you a little bit better. So these are the things that are in E or F. So let's start at the small end. 1 is in F, 3 is in both. All right, 5 is in F, 6 is in E, 7 is in F, and 9 is in both. All right, so if we look at how many elements are in there, 1, 2, 3, 4, 5, 6, looks like there are 6 objects or elements. Now we're looking at a 10-sided die, so this is out of 10. If we were going to draw it out, there would be a few things that are not in E union F, okay, and those would be, let's see what numbers are missing, 2, 4, and 8, and 10. So not in E and F are E or F are those 4 numbers, all right? So what is the probability? Clearly, the probability of being in E, U, F is 6/10 or 30%, if you like. Now, the book has a formula that says the probability of being in E union F is equal to the probability of being in E plus the probability of being in F minus the probability of being in both. That would be the intersection if you're in both, right? So let's see if this works numerically, and then let's make sure we can see why this works, okay? So the probability of being in E is clearly 3. There are 3 elements in E, so there are 3 in 10 are there. Your probability of being in F looks like it's 5 in 10. If you simply added those up, you'd have 8 things. That would be too many, all right? So how many things are in the intersection of those? We didn't write that out, but the elements that are in both are these 2. So there would be 2 elements that are in both, right? So if we subtract that out, then we suddenly have 6/10, which is the right number. So let's draw this out and make sure we understand why it comes out to be the way it is. So this will be all numbers from 1 to 10, all counting numbers. Things that could show up on a die. This will be set E, this will be set F, and we've already determined that 3 and 9 are in both, all right? So we have then also 6 over here, and then we also have 1, 5, and 7 over there, and the numbers that didn't make it into any set would be 2, 4, 8, and 10. They're in neither E or F. Okay, so that's what the diagram would look like. And if we count up how many things are in E, we obviously have 3 of them. And if we count up the things that are in F, we have 5 of them. But 3 plus 5 is 8. The problem is we've counted the 3 and the 9 twice. So the things that are in the overlapping region were doubly counted. So when we subtract the probability of being in the intersection of the two, we're removing one of the double countings. Okay, so you can easily see that 3 and 9 are included in both the probability for E and the probability of F, and so we have to subtract it out once since it was doubly counted. This is like finding the area if you had some like 2 rugs and you knew that how the area of each, but they were going to be overlapping and you wanted to find out the area of the floor that was being covered, you would have to, this area in the intersecting region would have been counted twice if you simply add the area of the rugs. So you have to subtract the intersecting region once in order to get the total area covered by those 2 regions. So it's very similar to that. Now, if we look at example 2, we'll see this is different. If we look at event E, so now we're looking for multiples of 4 or a prime number. So event E, the set would look like this. It would be 4 and 8. And you can see neither of those are prime. So F are the prime numbers. 1 is not a prime number. Feel free to look that up as to why it's not a prime number. 5, 7, those are the prime numbers, I believe. 8, 9, yep. Those are the prime numbers, all right? So we can see there's no intersection. So E intersect F is the null set, all right? So if we try to figure this one out, okay, the probability, I'm using the book formula, the probability of being in E or F would be, the probability of being in E minus the probability, or plus, I'm sorry, the probability of being in F minus the probability of being in E and F. But in this case, that's 0. So we don't have to subtract it out anymore. So when there is no overlap, we can simply say, well, this is 2 in 10, and this is, looks like 4 in 10. So we have a 6 in 10 probability that the event will happen, that we either get a 4 or a prime number. Okay, so we could draw that real quickly. We draw the whole thing. There's no overlap. There's a 4 and an 8, a 2, 3, 5, and 7. Looks like 1, 6, 9, and 10 are on the outside. And you can see, this would be a good chance to use the example of the complement, all right? So 4 in 10 are not in E union F, okay? So the probability of being in E union F would be 1 minus 4/10, which is 6/10, which is exactly what we just got, okay? So when you have an or statement, if there is no overlap between the events, you can add them up. You can add the probabilities up.